I'm Narita Hirokazu, leader of the Resource Circulation Technology Research Team. We seek to develop new separation and recovery technologies to recycle critical metals. To achieve carbon neutrality, we need a stable supply of critical metals, which are key to producing neodymium magnets and lithium-ion batteries used in EVs. In Japan, efficient recycling of such metals is needed because we depend on foreign countries for most of them. We have been developing highly efficient, low-cost recycling technologies for critical metals. I would like to show you our 3 current research projects on chemically separating critical metals, as well as the AIST consortium for the strategic urban mining research that we are also involved in.
This laboratory is developing the recycling technology of neodymium magnets. Neodymium magnets are powerful magnets that a Japanese company invented. They are essential for electric vehicles. They contain critical metals, such as neodymium and dysprosium.
Recovering critical metals from neodymium magnets needs large equipment, and the cost of processing is high, so most of it is conducted outside Japan. That is why we are developing a recovery technology that can be easily used in Japan.
This is a reaction vessel for recovering neodymium and dysprosium. These 3 vessels are connected via this alloy diaphragm. This is a schematic diagram of the reaction vessel. We keep the vessel at a temperature of several hundred degrees Celsius and fill it with molten salt. Then we dip neodymium magnets in the middle of the vessel and apply voltage. We put electrodes into either side of the vessel and apply negative voltage. Here, when we apply the appropriate voltage to the alloy diaphragm, the neodymium and dysprosium that dissolved from the neodymium magnets selectively pass through the alloy diaphragm and are deposited on the electrodes. This technology requires only one process, which significantly reduces cost.
At the current stage, we are researching the most efficient conditions. Meanwhile, we are working with companies to explore continuous operation and scaling up. Step by step, we are nearing industrialization.
This research focuses on recycling lithium-ion batteries. Lithium-ion batteries are in wide use, from mobile devices to electric vehicles. These rechargeable batteries changed the world. This black mass is cathode active material from lithium-ion batteries. Its constituents include lithium, cobalt, nickel, and manganese. We put these cathode active materials and carbon into a vessel and heat it to several hundred degrees Celsius. The carbon acts as a reducing agent, and we get compounds like lithium carbonate and cobalt metal. When we put the resulting sample into water, only lithium carbonate dissolves. We can use this to extract lithium ions with relatively simple chemical handling.
Conventional pyrometallurgy is a technology that can recover cobalt and nickel from cathode active materials, but not lithium. There is no choice but to dispose of it. By using our technology, we can recover lithium, cobalt, and nickel individually, and then recycle them into lithium-ion batteries. This low-cost technology has little environmental impact, so we promote partnering with companies to commercialize it.
Our third research theme is the design of new separation reagents. A separation reagent is a substance that can selectively recover a target element. We have produced many extractants based on our knowledge of chemical properties for critical metals and on practical techniques. An example is a diglycolic acid-type adsorbent, which recovers rare earth ions. The diglycolic acid can selectively capture rare earth ions. Meanwhile, this is a palladium extractant, thiodiglycolamide, which has been developed by AIST independently and is already in practical use. Our research will continue to establish technologies for developing separation reagents. For many years, AIST has carried out R&D on the efficient use of urban mines in society. The SURE Consortium plays a leading part. SURE stands for Strategic Urban Mining Research Base. There are nearly 60 apparatuses in the laboratory. Among them, AIST developed about 20, which can dismantle home appliances and such and sort them into materials.
Recycling from urban mines is essential for a resource-poor country like ours. So, AIST has established the SURE Consortium of over 90 institutions that research resource recycling.
For example, this is a computer circuit board. It cannot be recycled as it is because it has a mixture of many different materials. Using a SURE-developed apparatus, we can tidily sort the materials, as you can see. Next, look at these smartphones. A smartphone is densely embedded with many different materials in its compact body. It's a difficult device to sort physically. This automated sorting system can physically sort out various items, even smartphones. Even if you dump a bunch of different smartphones in at once, it can sort out the materials they contain according to the type of metal.
We call manufacturers arterial industry and recyclers Venus industry. Until now, only the Venus industry has recycled metal, but soon both will need to unite to recycle efficiently. SURE seeks to introduce this concept into society sooner. Recycling critical metals is growing in importance. This technology is essential to success in both carbon neutrality and sustainable development. Collaboration is vital to R&D on resource circulation technology. We would like to invite researchers in both the private sector and academia to contact us. Our research staff is eager to hear from you.